So in this video we're going to be talking about the electrical details of the input pin of a Teensy. So your Teensy has an equivalent circuit just like any other electrical instrument, even though it's a microcontroller instead of a big benchtop thing. I've included a picture of the equivalent circuit here, which I pulled directly from the datasheet for the Teensy, specifically from the datasheet of this microprocessor. And it's totally worth your time to read page 37 of the datasheet where I found this figure. This is a more complicated equivalent circuit than you're used to, so we're going to break it down in this video. One of the reasons this circuit seems complicated is that there are a whole bunch of input pins which share the same measurement circuit. The simplified channel select circuit here shows a bunch of switches, and it implies that only one switch is closed at any time in the datasheet. That way you can reuse the fast measurement circuit to measure many slow signals by switching between them using the channel select circuit. So let's cover up all of the superfluous channels to focus on just a single pin. The measurement circuit has a charming alphabet soup of vocabulary indicating what it is. The ADC SAR engine is short for Analog to Digital Converter Successive Approximation Register, which is just a fancy way of saying that it measures a voltage on this node. We can cover that up too, and just remember that we're measuring the voltage at the node labeled V measured. That leaves us with a less complicated diagram, and we can actually break it down even further by noticing that there are three parts to this diagram. The leftmost circle, labeled external circuitry, is actually indicating stuff outside of the Teensy, so it's not really part of our input pin model, but we'll talk about it anyway. The rightmost circle, input impedance, should be comforting. It's just saying that the input of the Teensy looks like an RC circuit, which is something we can probably understand. The middle circle, input protection, has a bunch of components that you may not have seen before, but they don't affect the operation of the pin unless you're applying too high or too low of a voltage, or you're trying to measure a very small signal. We're going to take a closer look at each of these three circles on the next few slides. The input impedance circle is most similar to the equivalent circuits that you've seen before. It's telling you what a Teensy load looks like. And so when you draw an equivalent circuit for a Teensy, basically you're only going to draw the stuff in this circuit. Most of the equivalent circuits we've looked at up until now have just been resistive loads, which is to say they're only modeled as resistors. This pin is a capacitive load. You'll notice there's a capacitor between the output voltage and ground instead of a resistor. That means that having a Teensy as a load doesn't divide your voltage if your voltage is moving really slow. So you never experience voltage loading from a Teensy. So even though the Teensy input looks like a capacitor, we can't quite celebrate yet. It's still possible for our external circuitry to interact with that load in a really nasty way. In particular, it turns out the Teensy pin is really sensitive to the source impedance, which is why the datasheet includes some notes about the external circuitry. The Teensy needs to have RAS, the external series resistance, smaller than 5 kilo ohms to work. And it needs to have the product of RAS and CAS, which is the time constant of the external circuitry, less than 1 nanosecond. This is fine, but it means you can't hook a high impedance sensor straight up to the Teensy and expect it to work. It's also worth noting that we've added 1 kilo ohm of resistance in series with all of your Teensy input pins in order to protect them. That means that your driving impedance needs to be less than 4 kilo ohms because it's going to fall in series with that 1 kilo ohm resistor that we added. So that external resistor that I just mentioned works with the input protection that lives in the middle circuit here. The input protection circuit is made of a pair of diodes, which are the triangle devices that show up in this picture. You may not have seen diodes before, and that's okay. All you need to know about them is that they prevent the voltage at V80 in, which is here, from reaching a level that is unsafe for the Teensy insides. They clip the input voltage to 0 volts or 3.3 volts if the input goes above or below those values. However, the diodes have a side effect that whenever the Teensy is powered, they inject a tiny but random amount of current into the Teensy pin. So there's going to be plus or minus 1 nanoamp on that pin all the time. This means that if your input voltage at V80 in is very small, or your source impedance is very big, then your input voltage can be swamped out by the interaction between that leakage current and your source impedance, which will make it look like you're just measuring noise, a signal that wanders around kind of randomly. So this is another reason that you should pay close attention to the source impedance driving the Teensy. So in summary, the Teensy pin has an equivalent circuit like anything else, and you can go read about it on page 37 of your datasheet. But a quick highlight reel of that page is that the Teensy input has a capacitive termination, so you won't form a resistive divider with your Teensy input pin. But it has 1 nanoamp of leakage current, so you have to be really careful driving it with a high impedance driver or with a low voltage. And also, you further have to be careful because the Teensy pin demands that your source resistance is less than 5 kilo ohms, and that your source time constant is less than a nanosecond.